In this video, we are going to take a look at problem 7.74 from our book. It says, in the document Anthropomorphic Reference Data for Children and Adults, C. Fryer et al. Present data from the National Health and Nutrition Examination Survey on a variety of human body measurements. A half century ago, the mean height of U.S. women in their 20s was 62.6 inches. Assume that the heights of today's women in their 20s are approximately normally distributed with a standard deviation of 2.88 inches. If the mean height today is the same as that of a half century ago, what percentage of all samples of 25 of today's women in their 20s have mean heights of at least 64.24 inches? Okay, so all right, it says a half century ago, mean height of women in their 20s was 62.6. So 50 years ago, the mean height of women in their 20s was 62.6 inches. Okay. All right. Now today's women, right? It says in their 20s are approximately normally distributed with a standard deviation of 2.88. All right, so if the mean height today is the same as that of a half century ago, all right, so under that assumption, right, that would mean that it would be the same, 62.6. So I'm writing down all of these things to work this out, and I'm going to mark that as an assumption, right? We're have an assumption that the mean for today's women in their 20s, the mean height is the same as it was 50 years ago, 62.6, okay? What percentage of all samples of 25, so n equals 25, of today's women in their 20s have mean heights of at least 64.24. Okay, so we take a sample of 25 of today's women, right, and in their 20s, and we measure their heights, right, and take the sample mean. We want to know what's the probability that the sample mean is greater than or equal to 64.24. So probability, what's the probability that x is greater than 64.24? All right, so that's a lot of stuff. Okay, so 50 years ago, the mean height was 62.6. All right. And they give us the standard deviation for today's women in their 20s, right? The standard deviation of the heights is 2.88 inches. All right, and so this assumption, right, the assumption was that the mean heights today are the same as they were 50 years ago, okay? All right, and so we're going to find the probability that we get a sample mean that's greater than or equal to 64.24, all right? All right, so the very first thing that we have to do here is to find for n equals 25, right? We want to know the sampling distribution of the sample mean. So in other words, what we need to know is what is the mean of the sample means? What is the standard deviation of the sample means, right? So that's the first thing before we can calculate this probability. All right, so we know from studying the sampling distribution of the sample means that the sample mean of, or the mean of the sample means would be 62.6, right? Same as the population mean, and under that assumption. Okay. We also know, right, that the standard deviation of the sample means, right, would be the same as the population standard deviation, right, divided by the square root of the sample size, which is 25. So that's going to be 2.88 divided by 5. So that comes out to be 0.576. Okay. All right. So now that we know the sampling distribution of the sample means, we can turn to calculating the probability that a sample mean of 25 would have that a sample of size 25 would have a sample mean greater than 64.24. So let's see, okay. All right, so first off, let's draw a normal curve. And just roughly figure out where 64.24 would be located. We know that the peak or the hump of this thing, right, is right at 62.6. So that would mean that 64.24 would be slightly to the right of that. Although it really, it doesn't make a huge amount of difference. I just kind of like to draw the picture so that it is fairly accurate, or at least looks right. Okay, so we need to find this area under the normal curve, and that will give us the answer, right, to this probability here. Okay, so how do we do that? Well, we find the z-score, right? So z equals x minus mu over sigma. Here we're talking about a calculation of a probability involving the sample mean, so that's going to be these values, right? The sampling distribution of the sample mean, right? And we know that the mean of the sample means is 62.6. We know that the standard deviation of the sample means is 0.576. Okay. All right, and then we need the z-score for 64.24, right? That's the value for x bar in this case. So 64.24 minus 62.66, or just 6, right, over 0.576. So I'm going to calculate that out off screen and get 64.24 minus 62.6 divided by 0.576, and I get 2.85 on that to 2 decimal places. Okay. All right, so now what we're going to do is go to table 2, look up that z-score. All right, so in the table 2.85 would be here, and then 0.05 right here. So we get that 0.9978. 9978. All right, so we know that the area to the left, right, of 2.85 on the standard normal would be 0.9978. Likewise, the area to the left, right, of 64.24 on this distribution, right, would also be 0.9978. But that's not exactly what we want, right? We want this part over here, right? And so to get that part over there, we know that the total area, right, is underneath the curve is 1. So we would just subtract off the area that we don't want, right, from the total area. So we would get 2, 2, 0, 0, right, on that. Okay. All right, so that would be the probability, right, that that you would get a sample of size 25, a random sample of size 25 that has a sample mean of 64.24. Okay, and so we calculated what they want, but this idea that in this problem is pretty important, right? So if it's this rare, that's a pretty rare sample, right? That sample mean that happens. It only happens 0.0022% of the time, right? So that is unusual, right? To get a sample mean that's that high, right? So there's basically two things, right, that you could kind of say here. Number one is, okay, maybe this was just really, really lucky. Maybe I just you know, if I did a random sample and I got a bunch of people that were that tall, that's just a fluke, and I got a high mean. But it was really, really unusual that would happen. The other thing that you could say is, hey, well, maybe this assumption, right, that we made, right, that the women in their 20s of today, maybe they don't have the same mean height as they used to, right, at 50 years ago. And you would kind of, suspect that that could be very well be true. Okay. So that is one of the uses of inferential statistics, right, is to make calculations on that. All this work that we've done right here will allow us to make to calculate the probability that you would get a sample, right, of this nature from this distribution right here. Okay, so this is sort of the idea about hypothesis testing, which we will talk about in section 9. Okay, that's it for this problem.